In the largest sense, the brain is organized like a team. Within it, different areas work like members of that team. Each has its job. This racer's brainstem, for instance, awoke him this morning and will put him to sleep tonight. How does he remember each turn of the track? How does he recall the long stretch ahead? Memories are made possible by tissue that sits atop the brainstem. It allows him intense emotions. It allows him to remember. And covering it all, the outer layer of the brain, a wrinkled sheet of cells laid out in functional continents. In the back, a region that relays what the eyes see. Again, on the surface, but now at the top, a ribbon relays information about touch. The feel of the wind on the driver's face. The pressure of his hand on the wheel. And just ahead of that ribbon of brain, another whose job is to orchestrate movement, sending commands to the spinal cord, then along the arm to the hand, telling it to change gears. In front of it all is the driver's frontal lobe, part of his thinking, planning brain, that bundle of tissue which provides him with a strategy to win the race. No single area of the brain can win the race by itself. No single tissue can function without the help of the rest of the brain. The brainstem, the midbrain, and all those regions along the surface are in constant contact with each other, always active, even when the body sleeps. How do we know all this? Thanks in part to the fantastic tools that the modern-day brain detective uses to look inside the brain. The CAT scan penetrates the skull to X-ray the brain's structure, showing the location of actual brain tissue. The PET scan forms still pictures of the brain's activity. Its colors show which areas are most and least active. One of the newest tools for looking at the brain is based on an old and established technology, the EEG, or electroencephalogram, in which the brain's electrical activity is recorded from sites on the scalp. The new invention is a computer program. It translates those electrical signals onto an actual map of the brain. The squiggles on paper are transformed into colors.
Janet, now you're going to be looking at a checkerboard pattern repetitively flashed on this TV screen. I want you to keep your eyes focused on the center of the screen.
Okay.
With this device, we can see the electrical changes of a brain at work. The bright colors represent positive electrical charges. Jesse Salb, the inventor, is watching the brain process a visual image. The signal from the screen flashes into the eyes and then rushes through the brain like this. Slowed down, we can watch vision deciphered. First at the back of the brain in a burst of yellow and red. About 3/10 of a second later, we can observe activity at the top of her brain as she realizes what she's just seen. But how are such signals telegraphed through brain tissue in the first place? How do tiny brain cells communicate with one another? Jason is a living explanation.
After lunch, you need to take these pills.
Nope.
So why don't you go ahead and take them and let's get it over with. Well, I hope someday you don't have to take it. But right now you do.
No way, Jose.
Jason is like any other 10-year-old. He detests medicine. Unfortunately, his need for it is more critical than most children's.
Jason is suffering or we believe him to be suffering from a condition which is almost pure epilepsy. In other words, what we call primary epilepsy. Epilepsy is in some ways a caricature of normal brain function. It is nature's experiment on how the brain works. And when we look at a person in an epileptic seizure, it's really a distortion of what one expects normal brain function to be. But it does teach us a lot about the circuitry of the brain and how it works.
If we could penetrate a normal brain with a high-powered microscope and observe neurons in action, we might see them switching on and off in an orderly fashion. During an epileptic seizure, Jason's brain undergoes an electrical storm. The discharge begins in the center of the brain. Then the rest of his brain is switched on uncontrollably. For a few seconds, the storm encounters no resistance. It short-circuits every one of the brain's more complex functions. Movement, mood, thought, everything.
Most transactions in the nervous system are conducted as electrical messages, and the actual conduct of the electrical impulse across the junction between nerve cells is a chemical process.
In the brain, nerves never actually touch. They're separated by small gaps known as synapses. Chemicals released from one nerve ending attach to the surface of the next nerve ending and cause the nerve to respond electrically. There are two types of chemicals or neurotransmitters. One type excites the next nerve, causing it to fire. The other inhibits the next nerve from firing.
And we feel that in Jason's case, he has primary epilepsy, which we think is due to a relative lack of an inhibitory neurotransmitter system, allowing normal discharges to become abnormally dispersed through the nervous system. And during this time, his brain ceases its normal function. He loses contact, his eyes get glazed, he tends to drop forward, and then almost immediately his seizure is again over and he's back to normal.
He has the seizures at a time when you're least expecting it.
We had to stop Jason from riding his bicycle, which was very traumatic for him. I think he felt a sense of freedom in riding his bike.
Always had one hand on his shoulder when we're walking down the street or the swimming pool, everywhere we go, or going down them long steps out here. Because he has the seizures, and suddenly he has one in the middle of, forget it, you can cross the street with him. He'll have it right there in the middle of the street and stop traffic.
Jason has a problem in taking medication because there's been a number of medications that has given him terrible side effects. And that has traumatized him because he knows what the medication is doing to him.
You don't like it? Or it's okay?
I don't like it.
You don't like it? Because it doesn't taste good, or you just don't like to have to take it?
No.
Do you know the name of it?
Depakote, and I hate it, and I hate it, and I hate it. You have it in your hand.
Right. It's Depakote. Do you know where this medicine goes once you swallow it?
Yes, and I don't want to see it. I don't want to hear it.
You ready for this, Jason? Mm-hmm.
Jason stayed at Blue Ridge Hospital in Charlottesville, Virginia for 6 weeks under Dr. Dreyfus's care. One goal was to help him overcome his horror of medication. The other was to induce seizures through deep breathing so that the electrical discharges of his brain could be monitored. Dr. Dreyfus would then be able to prescribe the drug most appropriate for his epilepsy.